Exercise 41.17. This exercise is to be solved manually. Consider the region enclosed by the graphs of x equal to y squared plus 4y plus 1 and 2x plus y equals to negative 2. Part A, sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Part B, provide a calculus calculation that yields the exact area of the region. Part C, assess the correctness of parts A and B by examining for consistency between the two results. Part A, sketch a quality graph of the described region. Provide a graphic approximation of the area of the region. Alright, for starters, let's take a look at these two individual graphs and make a preliminary assessment so that we can decide what sort of coordinate system will ultimately be appropriate and fit everything on it. Okay, let's begin with this first equation and think about its graph. Now, in the past, we've looked at many y equals to ax squared plus bx plus c situations, and we have a well-known generalization for what sort of graph to expect for those. And this situation is really an inverse of that situation. Now it's x equals to a y squared plus by plus c type form. What to expect? Well, just sort of do inverse type thinking, and we should expect the graph of this to be a parabola. It should have a horizontal axis of symmetry. It will be a translation of x equals to y squared. It will open to the right, and we can even formulate the y coordinate of the vertex, similar as the other generalization, except for now it's for y, and that will be a negative b over 2a. So we start recording that, like about so. And now let's get specific about the y-coordinate of that vertex. We say it's the opposite of b over 2a. In this particular case, then, that would mean negative 4 over 2 times 1, known more simply as a negative 2. And from there we can go ahead and easily compute the x-coordinate just by substitution. So we've got ourselves a v vertex sitting at negative 3, negative 2. Okay, maybe just a very crude thumbnail of what we've got here so far to help us think about this a little bit. And so, looking like we've got a situation with a vertex negative 3, negative 2, about there, opening to the right. Okay, a little bit like that is our initial crude idea of what's going on. Now, the next equation there. Okay, this of course is a straight line. And we can get the intercepts just mentally here. We've got letting y equals 0, x will be negative 1. It's about there. If x were to be 0, y would be negative 2. It's about there. It's a line looking something like that. Okay, this is enough information to tell us. Let's sketch a coordinate system having quadrant 3 being prominent. And it looks like the kind of numbers here, negative 3, negative 3 or so, kind of small. I think it'd be a good chance to spread this out a little bit with a scaling of, say, 1 centimeter equals 1/2 unit. That would probably make a pretty nice and accurate graph. So let's go and set that up and sketch this. Okay, at this point we see that there are a couple points of intersection that will surely play an important role in this problem and would also complete our graph. So let's work on that for a minute. Let's see, keeping the reader up on what we're doing here. Let's go here and have our points of intersection calculation. Okay, at intersection, well, of course, the x-coordinates would be equal. And going back up here, we could take this one and rewrite it by solving for x, and that would mean subtracting y, divide both sides by 2. We could also have this look like x equals to 1/2 negative y minus 2. So now we can equate the two x's in this case, and that would allow us to equate this expression here, the 1/2 times negative y minus 2, to the y squared plus 4y plus 1. Okay, it's going to be a pretty routine quadratic equation. Okay, and we also notice that these coordinates, negative 3/4, negative 1/2, consistent with the graph. This point of intersection, a 1, negative 4, also consistent with the graph. So we keep going with confidence. Things are looking good at this point. Okay, how about getting a graphic approximation of the area of this region? I think I would like to take advantage of this long straight line boundary as part of some geometric shape. I think I'm going to go with a trapezoid here. So let me come out here, staying parallel to this line so that I will have a trapezoid set up here. I need at least two sides parallel. And I'll just sort of a dashed line in a starting point, and I'll finish it out later. Now, and by the way, since the axes are scaled the same, this is important. They're both scaled at 1 centimeter equals a half unit, so that I can have a trapezoid oriented any kind of way and still just be able to use the ruler for picking up the dimensions of all of the sides or bases or altitude or whatever. Okay, now these next two sides, let's see, I'm going to sketch this. Let's see, let me first sketch this one, this side. I'm just going to make it so that the little leftover there will fill a void, so let me move out just a little bit to there. I think about that seems to do it. Now over here, this time I need to make it so that this excess fills in whatever void I leave here. Just working visually, it's an approximation, and I'll say about that seems to look about right, so let's go with that. Okay, so now we make the statement that the area of the enclosed region is approximately equal to the area of this dashed line trapezoid. Okay, and like all trapezoids, that would mean average base times height. Remembering the formula for the area of a trapezoid. And in this case here, let's see what we have. Time to pick up the ruler. Base 1. Okay, about 8 centimeters, so that's going to be 4 units. Remember, 1 centimeter is a half unit. Second base running at about, say, 4.8 becomes, say, 2.4 units. The height or altitude of this looks to be about 4.4 centimeters, becomes 2.2 units. So then this is, let's see, we have here 6.4, and half times 2.2 is easy to do in our head, that's 1.1. So a little scratch work. Okay, it looks like it's about 7.0 square units. And that's our main purpose of this part A, so I want this to be very prominent, kind of jump off the page so that the person reading the solution knows where to look. Okay, part A, settled. Part B, provide a calculus calculation that yields the exact area of the region. Alright, what sort of strategy shall we use for an analytic calculation? Well, the first and most popular idea is to always try using thin vertical rectangles, and let's try that for a moment. Now this seems to present two issues. If we watch how the tops of the rectangles are being formed, we see that it is the red curve that defines the top of the rectangle, at least in the beginning. But then there's a change. The top of the rectangle then becomes defined by the blue line instead. Okay, that's going to create two integrals, which is okay, but we try to avoid that. Also, what about the bottoms of the rectangles? As we follow those along, we find those are defined by the red curve, which is already being used to define the tops of the rectangles. Okay, there's another little bit of an issue, but not insurmountable. We could, for the first part of it, split the region with its axis of symmetry and then just use half of those rectangles and double the quantity. Okay. However, maybe there's an easier way, and that would be to consider slicing this up with thin horizontal rectangles. Let's try that. Okay, now if we follow the right hand end of these rectangles, we see that in each case it's defined by the blue line. We then go and follow the left end of each of these rectangles and find that in each case it's defined by the red curve. This looks pretty simple. Let's sum up these thin horizontal rectangle areas. Okay, to make progress in that, we will need to formulate the area of a single thin horizontal rectangle. Alright, like all rectangles, the area will be its length by width. In this case, the length of the rectangle would be the x-coordinate on the right minus the x-coordinate on the left. And then the width of the rectangle in each case will be a little section of the y-axis we can call dy. Okay, I think we are ready to go. Alright, let's apply that strategy that we have devised here. We would have a definite integral, which is going to sum thin horizontal rectangles going from C to D, and that means the x right minus x left is a side of the rectangle, and it has a width of little dy. Okay, looking at our graph, we can continue to set this up and keep going. Our limits of integration, taken as our y-coordinates of the points of intersection, we'll have our lower y as a negative 4, our higher y as being negative 1/2. That right-hand x-coordinate, alright, well, we had previously formulated that equation for x in terms of y, and that would leave us with a 1/2 negative y minus 2. As far as the x left goes, we have that already explicitly available. That will be the y squared plus 4y plus 1. Okay, we could maybe simplify this algebra a little bit here. I think with all this negative signs throughout here, I can simplify matters a little bit by using this little principle of integrals, and that is I can change the whole sign of the integrand and compensate by reversing the limits of integration. So use that here. Okay, I think we can get an antiderivative without too many problems. Actually, before I start the computation, it's usually easier to compute when you have things in any kind of factored form, and I'm noticing a common factor of y here, and since it's cubic, I would really like to do a little factoring to make the arithmetic a little easier here. So let me make another step. Okay, time for some subcalculation arithmetic. Okay, ready to take these numbers back to the main computation line here. Okay, 343 over 48 square units. Alright, well, let's see what we think about that. Surely need to assess the correctness here. Part C. Assess the correctness of parts A and B by examining for consistency between the two results. Alright, let's do a side-by-side comparison of our graphic approximation and our calculus calculation. Looking back at that, that was 7.0 square units. Our calculus calculation. Okay, 343 divided by 48. To get an apples-to-apples comparison, we need decimal numbers. So let's say here, good old long division. Okay, it's about 7.1. Alright, this looks really good. 7.0, 7.1. So here we could take 10% of this and be 0.7. We're only 0.1 apart. So 1% would be 0.07. 2% would be about what we have here. So without exaggerating, these results are within 2% of each other. So that would surely be consistent. And therefore, then we believe that the solutions to part A and B are very likely correct. Alright, so there we are. Looking good, and we're feeling confident about the correctness of this with such good consistency as we've seen here. Great.